So in our previous class we are done with the last part of our discussion regarding the component which we had considered, and that component was a rotary machine and that was turbine. So we completed the two turbines, turbine which is type of axial turbine, and before that we completed axial and centrifugal compressors. So here our objective for today's discussion is to look into the examples which would generally be solved in this course of related to gas turbines. So the first example is related to centrifugal compressor, which says that determine the impeller diameter and width at the impeller exit and power required to drive the centrifugal compressor for given data. So there is some data given. As per that data we are known with N, which is speed, which is given to be 12,500 revolutions per minute. Mass flow rate is given as 15 kg per second. Pressure ratio is given as 4:1, and then we are told that isentropic efficiency is at 75%. Then slip factor is 0.9, flow coefficient which is phi at the impeller exit, so it is basically given as phi 2. Hub diameter at the eye is 15 centimeter. Axial velocity at the entry to and exit of the impeller. Okay, so we are given with axial velocity 1 and we are given with CR2. Okay, at the impeller exit. So this is given 150 meter per second. Okay, and then we are given with stagnation temperature at the inlet 295 Kelvin. We are given with stagnation pressure at the inlet, which is 1 bar. We are told that there is equal pressure rise. Obviously this is static pressure rise in impeller and diffuser. So we know that 1 to 2 is impeller and 2 to 3 is diffuser. So we would say that P2 by P1 is equal to P3 by P2. So this is what we would say so. So this is the thing which are given for solving this example. So we will solve. We are told here that we are given with phi 2, and phi 2 we know phi 2 is equal to CA2 divided by U2, or rather CR2 divided by U2. This is phi 2. So this is given to us, which is 0.3. We are not given with U, but we are given with basically this velocity, which is 150 meter per second. So we know 150 meter per second, we know phi is 0.3, then this expression helps us to give U2. Okay, so CR2 is given, which is 150 meter per second, phi is given, which is 0.3, so we can find out U2. So if we remember, then this is hub and then this is the centrifugal compressor. This is rotating in this direction. This is hub and this is 2. Okay, so we are told that this is for us, this is diameter of hub, D hub, and this is diameter, basically this is 3. So this is radius corresponding to that diameter D3. Okay, so this is 2. So this is D2. Since 1 to 2 is impeller. So now we know D2. We are supposed to find out few things, which is impeller diameters. So impeller diameter means we have to find out what is this diameter at the eye. We are supposed to find out diameter at D2, okay, or diameter here. Then what would happen is we can find out U2 is equal to pi D2N by 60. So N is given to us, which is 12,500 RPM. So knowing the n, knowing this value 60 and u2, we can find out, this is step 1. In step 2 we can find out d2 in meters, u2 in meter per second. So we get d2 out of this exercise. Then we are supposed to find out power required. Then we can find out power required as formula m dot into u2 square into mu, or our power coefficient. So this is given to us, and this rather slip factor. So slip factor is given to us, which is 0.9, m dot is given to us, which is 15 kg per second, u2 is known to us from step 1, and then this will give us power, okay, in kilowatt or watt, depends. Now this is found out, this is this one diameter is found out, and then we have to again find out width. So for that, to find out one diameter and to find out the width, we need to use the formula for mass flow rate. So formula for mass flow rate is basically rho 2 rho 1 CA1 into A1, which is equal to rho 2 CR2 into U2, sorry, A2. So these are the formulas for mass flow rate. This is in kg per second, where A1 and A2 are the different areas at the inlet and outlet. For area at the inlet, we would know one thing, which is hub diameter, which is this is known. So area at the inlet is this. So for that, A1 is equal to pi by 4 d1 square minus d hub square, and area at the outlet. So this is the approach for the fluid which is coming axially into the inducer. So for that, this area, which is this area in which fluid is getting admitted. So for that, we are considering the annulus area, which is pi by 4 d1 square minus d hub square, and for that we have area pi d2 pi d into w, which is width between this and next blade. So we have this as area at the outlet. So we can use these formulas. Mass flow rate is known. So here we know axial velocity, we know d hub, but we don't know d1. So let us consider m dot is equal to rho 1 CA1 into pi by 4 d1 square minus d hub square. D hub is known, d1 is not known, c1 is known, rho 1 is not known, but we can find out rho 1. So how to find out rho 1? So for that, we need to work out for the fact that we should know what is the pressure and temperature at the inlet. Once we know pressure and temperature at the inlet, we can use the formula P is equal to rho RT to find out density at the inlet. So we know we are given with stagnation temperature at the inlet. So T01 is given to us as 295 Kelvin. But we know that this is the stagnation temperature. We know also velocity, which is 150 meter per second. Okay, velocity C1 is 150 meter per second. So this is also known to us. Now we know the formula that T01 upon T1, which is equal to 1 plus gamma minus 1 by 2 m square. So this is the formula which we can use. For that, we need to know Mach number, but we can differentiate this formula, or we can disintegrate this formula in other factor, or in terms of, we can use this formula where m will be taken as CA upon square root of gamma RT, where T1 would be found out. But instead of that, we can also use this at this inlet, which is H1 plus C1 square by 2 is equal to H01, where H1 is CPT1 plus C1 square by 2 is equal to CPT01. So T1 is equal to C1 T01 minus C1 square upon twice Cp. Here T01 is known to us, which is 295 Kelvin, C1 is known to us, which is 150 meter per second, Cp is known to us for air, which is 1.005 kilojoule per kg Kelvin. So this helps us to give T1 directly without any solving nonlinear equation as what we would have done here. So these are the two methods by which we can find out this T1. But then we need to find out what is the density. So for that we have to take help of pressure. So we are also known that stagnation pressure is 1 bar. So P01 upon P1 is equal to T01 upon T1 bracket raised to gamma minus 1 upon gamma. Gamma for air is 1.4. T01 is known, 295 Kelvin. T1 is found out from here. So T1 is known, T01 is known, gamma is known. Then P01 is known, which is 1 bar. So we can get P1 from here. From here we got T1. So we got P1, we got T1. So we get rho 1 is equal to P1 upon RT1. P1 upon RT1. R is known for air, which is 0.287 or 287 joule per kg Kelvin. T1 is known to us from this step. So this gives us density. So now knowing the density, knowing the velocity 150 meter per second, knowing the mass flow rate, knowing the diameter of the hub, we can find out D1, which is the diameter at this state, which is the diameter. This is D1. So we know this is D1 diameter. Now our objective is to find out D2 or width W2. So now we know the formula that we have basically mass flow rate is equal to rho 2 A2 into rho 2 into U2 or C2 or CR2. This is the mass flow rate formula. Basically U means velocity. We have to keep some velocity which is normal to the area at the outlet, and for normal to the area at the outlet we have CR2 velocity. So m dot is equal to rho 2 CR2 and A2, where rho 2 CR2 into area is pi d2 into W. Mass flow rate is known, CR2 is known, 150 meter per second, and then this value is known, D2 is known to us, we have found out D2 rather, and then we just have to find out W2. So we have to find out W2. D2 was found out in earlier step where we had used U2 is equal to pi D2n by 60, but before that we have to find out rho 2. So to find out rho 2 we have to need pressure and temperature at T, pressure and temperature at 2. So for that we will take help of this expression which is given as constraint to us, which says that there is equal pressure rise in impeller and diffuser, and the pressure rise for the compressor is 4:1. So this P3 upon P1 is 4, but what is that? Equal pressure rise, so we would expect both to be 2. So P2 by P1 is equal to P3 by P2 is equal to 2. So this is what it is known to us. So we know that P3 is equal to 4P1. P3 is equal to 4P1 from here. Okay. So P1 is known to us, so we can find out P3. Okay. So knowing this, we can find out P2 square is equal to P3 into P1, but P3 is equal to 4 P1. So P2 square is equal to 4 P1 square. So P2 is equal to twice P1. Anyway, this was known to us. We know P1, which is static pressure. Knowing the static pressure, we can find out P2, which is the static pressure at the exit of the diffuser. Now our interest is to find out static temperature at the P2 is the static pressure at the exit of the impeller. So we should find out static temperature at the exit of the impeller. So we can use isentropic formula, which is P2 by P1 is equal to T2 by T1 bracket raised to gamma upon gamma minus 1. P1 is known, T1 is known, then P2. Then P2 is also known from here. We can find out T2, but this is ideal temperature, which is isentropic. So knowing this step gives us T2 dash, which is isentropic temperature. But we are told that isentropic efficiency of compressor is 75%. So we know that compressor efficiency is ideal work divided by actual work. So T2 dash is known, T1 is known, T1 is known, T2 is unknown. So for the unknown T2, knowing the compressor efficiency, we can find out T2. So thus we have found out T2. What is our requirement? So T2 is known, P2 is known, then rho 2 can be found out using the formula P2 is equal to rho 2 R T2. So P2 is known, T2 is known, we would find out rho 2. So rho 2 is known here, CR2 is known, pi value is known, D2 is known, pi dn by 60. So we can find out W. Okay. So here this example is this way solved. So the main thing what we should remember in this example is how to take area for mass flow rate calculation, which area is taken at the inlet and which area is taken at the outlet. We have axial inlet and we have radial outlet. So this is axial inlet, which is normal to the plane of the board. We have radial outlet, which is in the radius of the centrifugal compressor. Okay. So we will solve the second example, which is related to again centrifugal compressor. This example says that there is a centrifugal compressor which has an inlet eye which is 15 centimeters. So we are given with D1 which is 15 centimeter. Then impeller revolves at 20,000 RPM. So we are given N as 20,000 RPM, and inlet air has axial velocity CA1 is 107 meter per second. Inlet stagnation temperature is given 294 Kelvin. Inlet pressure is given, P01 is given 1.03 kg per centimeter square. So we have to determine the angle of the blade at the theoretical angle of the blade at the inlet. That means we are supposed to find out blade angle, which is beta 1 at the inlet. Okay, and then we have to find out Mach number at the outlet M2. So we are supposed to find out Mach number of the flow at the tip of the eye, but this Mach number is M2 at the tip is basically related to relative velocity basis. So this is basically MR2 relative to. So this is what we have to find out. So now for this all sake, let us try what is given to us. We know that velocity triangle for the centrifugal compressor at the inlet is, this is our CA1, okay, this is U1, so we have this as V1. So this is our velocity triangle. So we have alpha as 90 degree and we have beta 1. So this is known to us. So now having these things known, we can find out basically this is C1 is equal to CA1. CW is 0 at the inlet. So U1 is equal to pi d1n by 60. We are known with d1, we know n, and then we can find out u1. So u1 is known, and this velocity triangle u1 is known. We are given with again axial velocity, which is this. So this is known. So we can find out this, we can find out this. That means we can find out beta. So which says that tan of beta 1 is equal to CA1 divided by u1. So we know that beta 1 is equal to tan inverse CA1 upon u1. So we know the first point, which is theoretical angle of the blade at the inlet, at the entry. So this is known to us. Now we have found out the first answer, which is this. Now we are supposed to find out the second answer, which is Mach number of the flow at the tip of the eye. So for that we have to find out basically V2, which is velocity at the outlet. Once V2 is found out, we can find out the Mach number, which is V2. So basically formula of Mach number MR2 is V2 upon A2. So V2 upon square root of gamma R T2. So we should know basically V2 and T2 for this all fact. Once we know V2 and T2, we can find out MR2. Here we are said that we have to find out Mach number at the tip of the eye. So basically we have to find out not 2, we have to find out 1. So since this is 1, this is again 1, and this is again 1, this is 1, and this is 1. So we have to find out MR1, which is V1 upon A1. So which is V1 upon under root gamma R T1. This Mach number we can find out here. Now we have to find out V1 first, and now V1 can be found out since beta is known to us. So V1 is equal to U1 upon cos of beta 1. So beta is known from here, from step 1, U1 is known before that, then we know V1. Now our problem is to find out T1. For that we can again take help, and then we can find out H01 is equal to H1 plus C1 square by 2. So T01 is equal to T1 plus C1 square by 2 Cp. So here we are supposed to know T1. So T1 is equal to T01 minus C1 square upon twice Cp, where we are told that stagnation temperature at the inlet is 294. So this is known. Velocity, axial velocity is known 107. Cp is known for the air. So this is constant. So this is known to us 1.005. So knowing these things, we know T1. So we know everything in this formula, and we can find out what is the Mach number, relative Mach number at the tip of the eye of the compressor. So the example, next example says that air at 1.0132 bar and 288 Kelvin enters an axial compressor stage with an axial velocity of 150 meter per second. So given thing to us is CA1 is equal to 150 meter per second. There is no inlet guide vane. So this CA1 is equal to basically C1. The rotor stage has a tip diameter, d tip is equal to 60 centimeter, and hub diameter d hub is equal to 50 centimeter. These things are given to us, and it rotates, basically speed is given as 100 rps. Air enters the rotor and leaves the stator in axial direction with no change in velocity and radius. The air is turned through 30.2 degree as it passes through the rotor. So we are given with deflection. So we are given with beta 2 minus beta 1 as 30.2 degree. Okay, assume a static pressure rise of 1.2. So we are assuming that there is a static pressure rise as 1.2. We are told to that. And assuming constant specific heat and that the air enters and leaves the blade at the blade angles. Okay, construct the velocity diagram at the mean diameter of the stage, mass flow rate we have to find out, pressure required and degree of reaction. Okay, so we have to first find out, first we have to draw the velocity triangle. So we know that this is the blade so for the blade V1 and then we have U1 and then we have C1. Okay, U1 and then we have C1 is equal to CA1. Then for that all sake we have this as V2 and then we have this as C2 and then we have this as U2, but here we have CA2. So this is the velocity triangle for us. Now here we are supposed to find out, first we have drawn the velocity triangle. Now we are supposed to find out what is the mass flow rate, but before that we would try to make the angle. This is beta 1, this is alpha 1 is equal to 90 degree. Why did we draw like this? Since we are told that there is no guide vane. So since there is no guide vane, that is why it is coming directly in the axial direction. So absolute velocity is in the axial direction since there is no guide vane. It is mentioned over here in the example. Having said this, we are now saying that this is beta 2, this is alpha 2. Okay, so we would first say that u is equal to pi dn. Before that we should remember one thing, that in case of compressor we know this is hub and then we have this as rotor and then we have this as stator. Okay, and then we are given with this as hub diameter and we are given with this as tip diameter, but we should always work with the mid height of the blade. So our all calculations belong to the mid height of the blade. So we have to take mean of these two diameters to find out this mid height of the blade. Since we have drawn the inlet velocity triangle here and we have drawn outlet velocity triangle over here where there is no change in radius as it is suggested. So u is equal to pi dn. We would have used by 60 in this formula if we would have given n in rpm, but we are given n is rps. So this is pi dn. So but here we can use is here as d1 d tip plus d hub by 2 into n. So we know n, we know these two diameters, so we can find out u from here. Okay, so we know now u. So knowing u, we can say that we can find out beta 1. We know u, we know c1 which is ca1 which is 150 meter per second. So in this formula we can say that tan of beta 1 is equal to ca1 upon u1. So here we know ca1, we know u1, we can find out beta 1. But then we told that beta 2 minus beta 1, which is a deflection of the flow, is 30.2 degree. So we get beta 2 also from this formula. So beta 2 is known to us now. Now this is complete U2, this is U2 here, and we know now beta 2. Okay. We are also told that there is no change in direction and velocity. With no change in velocity and radius. So we basically say that CA1 is equal to CA2. There is no change in axial velocity. So CA2 is known to us. So CA2 is known to us. So we can find out this distance. This, let us say this distance to be x. So x is equal to, we know that this distance is CW2. So x is equal to basically tan beta 2 is equal to x divided by CA2, and that way we can get x from this formula since we know beta 2. Now since we know x, now we can know U2 minus x, which is rather CW2. Now knowing the CW2 and this, we can know CW2, we can know tan alpha 2 is equal to CW2 upon CA2. So we can know from here what is alpha 2. We know what is alpha 2 from this formula. So knowing this, we can take use of other parameters and we can find out which is mass. Basically these things will be useful for us to find out power required. So before that we can find out mass flow rate, and mass flow rate is pi by 4 d tip square minus d hub square into Ca into rho 2. So this is the formula for our mass flow rate which is supposed to be found out. So for that we should know rho 2. So for that let us find out, we are given with basically pressure ratio so that we can make use of. We are told that there is some pressure and temperature and velocity. So we know that T1 is equal to, we were using this formula, minus C1 square upon twice Cp. So this formula is known to us. Here we are taking this as static temperature, which is, they are taking it as total temperature, and we are taking it as velocity, which is 150 meter per second. So knowing these two things, we can find out T1. Okay, but we know that T2 upon T1 is equal to P2 upon P1 bracket raised to gamma minus 1 upon gamma, but pressure ratio is given to us as 1.2. So this is 1.2 bracket raised to gamma minus 1 upon gamma. Within that T1 is known to us. So since T1 is known to us, we know from this formula what is T2. So we know now basically T2. So T2 is known to us. Knowing the T2, we further knowing the P1 and P2 by P1, we can find out P2. Okay, P2 is also known to us. Now having said this, we can further make use of rho 2, which is P2 is equal to rho 2 or T2. We can find out rho 2 from this formula. So once we know rho 2, once we know T2, we can, once we know rho 2, this is known, everything is known, we can find out m dot. So this is how we can find out m dot. So once m dot is known, we can use this to find out power required. Since for power required, we have power required which is equal to U into Ca into m dot into tan of beta 1 minus tan of beta 2. This formula is known to us. U is known, Ca is known, Ca1 or Ca2 is same, m dot is known, beta 1 is known, beta 2 is known. So we can find out which is power required. So then we can find out degree of reaction, which is Ca upon twice U into tan of beta 1 plus tan of beta 2. So here again Ca is known, U is known, tan beta 1 is known, tan beta 2 is known. We can find out degree of reaction. Power will be in kilowatt. Degree of reaction is a non-dimensional number. So we have just solved this example for axial compressor. Okay, so this is how we have solved the examples for compressors. So we have to work first with drawing the velocity triangle. We have to mention the given quantities along with the velocity triangle. We should know the parameters of the compressors, and then we can solve the example for the compressors. Thank you.